This is the title. Now, today we will talk about inverse problem of finding right-hand side and also some coefficients of diffusion equations. And novelty here is that these unknown functions depends both on time and some part of spatial variables. This kind of issue was considered not just a few works, and we recall them later. But now I want to say that there is a method proposed by Lyons to solve initial boundary value problem for nonlinear equations. The interesting thing is that the same method can prove this inverse problem to show uniqueness and existence. When we apply Fourier method, we use some original idea from this paper of Bubnov. Okay. Our report is based on these papers with my colleague, Muhodinova Akila, and from Tashkent State University Information Technology. And first paper is published and all others not yet. And I will talk in details about work 2 and then just list results of other papers. So we'll consider the following initial boundary value problem. 1. Here d alpha, it is Gerasimov-Kaputov derivative. X is m-dimensional vector and y is n-dimensional. And when h is known function, then we call it forward problem. But in our case, h we assume unknown and try to find h by using overdetermination condition 2. So if h depends only on t or only on spatial variables, there are quite a lot of papers, but the case when h depends both on t and x, just a few papers published. And first of all, we should note that in all known papers, overdetermination condition is taken in the form of 3. And we also considered the same condition 3 in our paper 1. We note some known papers, especially this paper 5. Here they considered hyperbolic equation and they proved only uniqueness of unknown function. And paper 6, they provide numerical solution of this problem. And now when alpha is equal to 1, this is diffusion equation, and our results are new for diffusion equation as well. So in paper 7 and 8, they consider inverse problem just similar to ours, but the domain, this x and y, is taken from half space, and this fact plays very important role in the proving of this solvability of this inverse problem. And also we note these papers 9 and 10. 9, this Yamamoto and colleague, they considered fractional differential equation with alpha from here. And in 10, they considered parabolic equation. So in paper 9, again, y is one-dimensional. And for gx, there are certain conditions. And using this Fourier method, problem was reduced to integral equation. And then authors applied compressed mapping method. And they proved existence and uniqueness of h, but about coefficients, they only proved stability of this coefficient. And paper 10, it's an interesting paper. They considered simultaneously determination of 3 unknown coefficients, the coefficient of the time derivative and 2 lower coefficients. But again, here x and y one-dimensional, and this is important role it plays. and they used weak approximation method. This puts very strict condition for solution of forward problems, that you can apply this method if and only if solution of forward problem has 12 derivatives, even 12 derivatives. So this is first thing. And second thing, again, they considered y is from R1. And when we will show here in this talk, when with growth of n, the requirement for smoothness of the problem's data increases. So that's why, and also some problems makes with growth of n. Okay, so we consider weak solvability, and what we do is we take the equation 1 and multiply. We want to use this overdetermination condition. We multiply by omega from overdetermination condition and integrate over domain omega. Then we have this equation, and from this equation we can find h. H will have the following form 5, but problem is that h depends on solution of forward problem, u. So this is definition of weak solution. So a pair of function, to find pair of function, u and h has form 5, and u satisfied all these conditions. And instead of differential equation, we consider integral differential equation with arbitrary v. Now, to formulate our main result here, we need to recall some properties of eigenvalues of Laplace operator. So we consider the following spectral problem, and when we apply to our problem Fourier method, we'll come to this spectral problem. Anyway, right, it has the main property which we want to use. This series converges if A is greater than n and a half. That's why we can denote this constant with some C epsilon. So proof of this you can find in this book. Now, we also use this property 9. You just take eigenfunctions and then apply Green's identity, and you got 9. In general, this scalar product equals to this. And we also define the degree of Laplace operator by using spectral theorem in this way. And in the domain of this operator, we introduce the norm as follows. Now, we have also functions depending t and x. Here we use the following notation. Here, what this notation means that tau means this, you differentiate with respect to y, tau times, and with respect to x, just L2. Now, this is a Mittag-Leffler function. It is bounded if argument is in some segment, and this m depends on b. We introduce these two numbers. Just remember these two numbers. And this is main result. So let epsilon be any positive number. And if this f, g, and so phi satisfies these conditions, then there is a unique weak solution. And moreover, this solution satisfies these estimates where kg depends on the data of problem. Okay. This is just all other smoothness conditions. The main condition is number 4. This number should be less or equal to 1. So how we can achieve this? We can achieve this, for example, if we take this number small, or the easy way, m alpha takes small. What is it, m alpha? M alpha is, in fact, t, capital T. So if we take capital T small, then we have a weak solution. But since this condition 4 doesn't depend on initial functions, so we can solve problem first in this interval till T1. T1 is small. Then take T1 as an initial condition and solve this problem in this interval, and so on. So we have global solution. Okay, now a priori estimates. we look for solution in the form of 17. Vk is these eigenfunctions. Uk is unknown functions. And then if we use for definition of H, this formula 17, then H will have the following for. Again, H depends, you see, on all UGT. So now you put this F, G into Fourier series and put to definition of weak solution, then you will have this equation 20. Here we use this, to get this one, we use for scalar products this, which we mentioned above. Now, equation 20 is an integral differential equation. We have for this equation initial condition and also boundary condition. That's why it's a very nice equation. But challenge is here that H, as you see here, depends on all UG here. So you have system, in one equation you have all of this UGT. How to solve this system? Here we use the idea of Bubnov, and we construct the following recurrent relations. 21, we put right hand side u I minus 1, left hand side ui, and then show that uki tends to uk. So what we do is we obtain a priori estimate this lemma about this. Let epsilon any positive number. If you have 23, then you have 24. 23 is just the condition from the theorem. Okay? So how to prove this? Just some idea, because it is quite complicated. And you see, we take recurrence relation, and instead omega we put uki. In that case, we have the following equality. And then here, for first guy here, we apply Alekhanov's estimate and this estimate, and we obtain 25. And right-hand side, we estimate right-hand side. We don't stop here, just omit it. The only thing is that this C epsilon, which we noted above, is appear here. When you take summation of these eigenvalues, then you have the C epsilon. So eventually you have the following estimate. You see, second guy and third guy, they're positive. That's why we can omit them. And then we have the following estimate. And for this estimate, we again apply Alekhanov's lemma, another lemma in the same paper. If you have this estimate for derivative, then function, it has the following estimate. Using this, we got this one, and then take summation and multiply by lambda g, and you have this inequality. And using this, this number on the right-hand side, this is A0, and this number, according condition of this lemma, is less than half, then you have this estimate 29. And now, instead of uk, you put 0, you obtain for u1, put here u1, you get u2, and so on. And you have the statement of the lemma, 31. And nearly similar arguments apply, and then you get estimates for derivatives and for fractional derivatives. And we can show that these sequences are fundamental, and then we can obtain convergence here, and then we can pass to the limit in the equation of for the weak solution, and then we got the following. So this means that U, which we found, and H, which defined by formula, satisfied all conditions of definition 1. That is, theorem 1 is proved. Now, this first paper, in the first paper, we considered the following condition, over-determination condition, instead of this. As I noted above, all other papers considered over-determination condition 31. So what we showed in this paper that, in fact, just in one word, this condition is better, because if you take this condition, you must require a lot of conditions for data of the problem. So it was shown in this paper. Now, next paper, we consider some nonlinearity here. You see, this G right-hand side depends on U, and also the same integral condition. Now you cannot apply here Fourier series because nonlinearity. That's why we applied Galerkin method. So we look for solution in the form of 37, and these are unknown coefficients, C, G. There's just some functions which is dense in L2. So if omega, F, and G, and H satisfied all these conditions, then you see for G it is standard Lifshitz condition. Then you have unique solution, unique weak solution for this problem here, and also these estimates are satisfied. Okay, now, and this paper 4, we consider another inverse problem, such that here unknown is this one, coefficient in front of U. So to solve this problem, we use the following overdetermination condition, 46. Now you see, pay attention, M is less or equal to 3. Why? Because we in the proof apply this Sobolev inequality, and here L4, here Sobolev space. Here you can use this only if M is less or equal to 3. Now we introduce the following numbers. This and this, you see, this means that phi has one derivative with respect to x, and tau one derivative with respect to y, and same for all others. Tau 1 and tau 2 has this form. Okay, now this is theorem. You see, once this since this problem is nonlinear, then we have first theorem about local solvability. So if these conditions satisfy epsilon any positive number, then we have unique weak solution, and this solution satisfies these conditions. So here you have capital T. This condition is the main condition, and the capital T must be small. That's why this is theorem about local solvability. We also have result for global solvability. For this, we use inequality 51, Poincare inequality. And CP, optimal CP is 1 over lambda. Lambda is first eigenvalue. And you see, using Rayleigh quotient, you can show that if omega measure of omega tends to 0, then lambda 1 tends to infinity, and this coefficient will be as small as you want. Okay, now this theorem about global solvability. So if instead of conditions 4, 5 of theorem 11, you have these conditions, then solution exists globally. Here we see this condition is main condition, CP, which is there, should be small. That means the domain for X, it should be small domain. In that case, you have global solution. You see, everywhere above, we had epsilon. The question is why? The thing is that taking epsilon bigger, we can get everywhere above in all results, not only weak solution, also strong solution. How we do is, we just show for last theorem. So this is definition of strong solution. Weak solution is of the problem is strong solution if these conditions satisfied and equations holds almost everywhere. So main condition is this. So this must have second derivative. So we can achieve that with taking epsilon big. So if epsilon is 5 in theorem 11, then this solution, this problem has global, local, strong solution. So And this solution has the following estimate. Here, when you take epsilon 5, then r equal to this. So first derivative with respect to x, and this much derivative with respect to y. Same there. And this is about local solvability, but the same way we can apply for theorem 3 epsilon equal to 5 and get a strong global solution. So thank you very much.